Okay, so we're on chapter 2.2. We're talking about graphing functions. We've got a definition here. If we have a function f with a domain, and the graph of f is that set of ordered pairs, where you have a first component x, a second component f of x, where x is an element of your domain A. And we plot that in the coordinate plane. Now, what I have here is three examples, and we'll talk about graphing these three examples just simply by plotting points. Plotting points means we choose a value of x, we find a value of f of x, which is of course dependent upon excuse me, our choices of x. So we got three functions here. Let's go ahead and look at them by plotting points. So I'm going to create a table of values, x comma f of x. Okay. So this is my independent variable. This is my dependent. What f does is it tells us a rule. Whatever we put in for x, in this case, we're going to take that value of x and square it. You're allowed to put any inputs that you want in for x at this point, because there's no restrictions on what we put in for x. So I'm just going to put in a couple and just get a sense of the idea of what's going on. If I put in -3 here for x, so we'll get -3 squared, that gives us 9. -2 gives us 4. -1 gives us 1. 0 gives us 0. 1, 1, 2, 4, and so forth. Okay, and this will get 3, 9. If we graph these points here on the coordinate plane, 0, 0, 1, 1, 1, -1, -1, 1, 2, 4, 3, 4, and so forth, -2, 4, and we continue to graph this, we get the graph of this parabola, and this is a function that we've got to kind of memorize. It's going to be one of those ones in our library, which we'll talk about shortly. So f of x equals x squared. This is simply the graph of f of x equals x squared. It represents all these points that are here, and there's an infinite number of points on this graph. All these correspond to a coordinate that satisfies this equation. All right. So again, there's an infinite number of these, and any one of these points is said to satisfy this equation. Any one of these points, x comma f of x, where we have an x-axis and an f of x, or a y-axis. Okay. This is an example of a parabola. It's also an example of one of the types of power functions. This is a linear function here. It's a linear function because it has the form y equals mx plus b, as you will recall from your algebra days. So if we put in x's and we find out what f of x's are, for example, suppose I plug in, say, -2. 2 times -2 is -4, -3 is -7. Put in, say, -1, -2 minus 5, right? I put in 0, and I think we get -3. And again, you can put a number of points in until you get the idea of what's going on. And at that point, you can stop, put in 1, and I think we get -1. We know this is a line. We know it creates a linear function, 2, -7, 1, 2, 3, 4, 5, 6, 7. Some point right here, -1, -5. Okay, gives us a point about right here. 0, -3. Okay, 1, -1. And we've got this line here that looks something like that. Okay, this is an example of a linear function. So we got power function, okay, linear function, and this over here is what we call a constant function. Okay, a constant function, because it doesn't matter what we choose for x. Okay, if we have x, f of x here, I put in x to say 7. What's f of x? Well, f of 7 is still 3. If I put in, say, -1.1, f of -1.1 is 3. Doesn't matter what we put in for x, we still get 3. If I put in -3, if I put in 4, we're always going to get an output of 3. And what this says is, no matter what our x value, our height of our function, our height of our function is always 3. So we're going to have a bunch of these points right here that have height 3. -1.1, 3. -3, 3. 4, 3. And all these points create what we call a constant function. That looks something like that. So now what we're going to do is we're going to look at the different library functions that we're going to need to know for this class, just so that we have them in our kind of data bank that we're ready to pull up at any time. Okay, so I have here a library of functions. What I'm going to do is I'm going to go through each one and talk about them. The first one that we have is the linear functions. This is a subset of them, f of x equals b. This is a subset of when it's particularly a constant function, so it's constantly at the same height. Again, these could be at any height, but for example, this might be one of them. Maybe this is f of x equals 2. It says height 2, okay? So again, there's a family of functions that have constant height. Could be f of x equals 2, f of x equals negative 4.3, whatever. There's an infinite family, but in general they have the form f of x equals b. Okay. We also have linear functions. Linear functions have the form f of x equals mx plus b, where m is slope and b is the y-intercept. We've got a family of functions that have the form that look like, depending on what the slope is, there's a family of functions that have positive slope going this way, and a family of functions that have negative slope going this way. Okay, these also, again, this is a subset of these type. This is a subset in the sense that these are particular when m is 0. In this case, when m is 0. Okay, so those are our linear functions. Okay, those are all functions. We also have power functions, and we separate them into two types. When n is even and when n is odd. Okay, so think of this one as like f of x equals x squared, or f of x equals x to the 4th, or f of x equals x to the 6th. So that exponent there is an even number. Now, if it's an even number in general, what they're going to do is they're going to look like a parabola. Okay? Okay? And as n increases, outside of 1 and negative 1, these things get steeper, but inside of negative 1 and 1, they get flatter. So it's kind of like, as we increase n, these things get really steep here, but then they get flatter, just flatter right around here, okay? So they become more flat, and then they get steep like this, okay? So, depending on what n is in terms of what even number it is. Again, it accelerates faster when n is an even number that's higher, and it doesn't accelerate as fast when n is just like 2 or 4 or whatever. All right, f of x equals x to the n. This time n is odd. Well, these guys look particularly like this, kind of this S-shaped deal, okay? And you'll note that, similar to when f of x equals x to n when n is even, these things, as n gets bigger oddly, so oddly mean, I guess, 3, 5, 7, 9, x to the 9th is going to be more steep here, okay? And it's going to be flatter underneath over here. So it's going to be, underneath here, but above here. If n is a larger number, that's odd than it is if it's a smaller number, that's odd. So this is a family of functions that have the form f of x equals x to n. Again, these are both types of power functions. They have call them power functions because they have these n as their exponents. Root functions are kind of cool. So we have root functions. If we have f of x equals the nth root of x, we know that if n is even, we can't have a negative value for x. So that restricts us, restricts our domain. Turns out these functions have the form that look like this. They're kind of slow growing. And that should kind of make sense because suppose I put in, say, a really large number like 100 for x. Well, what's the height if n is 2? So we're talking about the square root function. Well, if x is 100, the square root of 100 is 10, right? So if I have 10, what's that mean? Well, 10 means that the height is 10. So if the x value is 100, the y value is 10, or the f of x value is 10, that means it's going to be really far this way and only a little bit up. Even if we increase great numbers on the x, we'll only get slightly higher. And that's why this thing kind of flattens out, if you will, as x increases, okay? Now, if we have the nth root of x where n is odd, well, now x's can be negative. We can take, if this index here is odd, we can take the nth root of a negative number. So what this does, this makes us have a function that kind of looks like that S shape, similar to what we had over here, but just going a different direction. And it looks something like this. Okay? So these are the root functions. And what I do is I encourage you to play around with this. For example, just play around with it. Take an example and look at, like, say, f of x equals, say, the third root of x. And what you should do is you should look at, hey, let's see what happens when I look at a table here. X comma cube root of x, and see what values of x, given a value of x, see what the outputs are, and see what that kind of graph looks like, and you'll convince yourself that it looks similar to this. Okay? Reciprocal functions. What they do is, and I actually call them, when n is even, I actually call it the Atari function, and the reason I call it the, oops, I got the wrong color. I call it the Atari function because, you know, well, it looks like Atari, if you will, the Atari symbol. So when n is even, this thing's going to be asymptotic to both the x-axis and the y-axis here, and it's going to look something like that. However, when n is odd, it does take on some negative values. Oops, that's wrong. Sorry. When n is odd, it's going to look something like that. Okay, it's kind of like that Hurley symbol or whatever that company is. Okay. Yeah, reciprocal functions. All right. The absolute value function. What does it look like? Well, the absolute value function looks like a v, if you will, and it's going to have something of this form. I think most people are aware of what the absolute value function looks like, and it's kind of a cool looking function. Notice that these are really just rays emanating from the origin. Okay, and then lastly, we've got the greatest integer function. Well, the greatest integer function talks about what's the greatest integer that you've most recently passed. For example, if I take, say, any number between 0 and 1 inclusive, or 1 exclusive, I get the height of 1. But if I take, say, the point 1, my output is 1. And some people call this the step function for what it looks like. Okay, but it's called the greatest integer function because we're always taking the greatest integer that you kind of most recently passed. For example, here we have, say, let's take this value. This is the x value 1.5. What's the greatest integer that you passed if you're at 1.5? Well, the greatest integer is 1, right? So that's why the height of it is at 1. But as soon as I creep up to 2, then all of a sudden my height is 2. 2.1, 2.5, 2.9, and so forth. My height is going to be 2, but as soon as I get to 3, then I bump up. And this goes on indefinitely in both directions here in terms of what it looks like. It's called the greatest integer function or the step function.